Hello everyone. Today we are going to see about the measure of ductility in tension test. First, we will examine the meaning of ductility. Ductility is a qualitative and subjective property of a material. Ductility is nothing but it is a mechanical property of a material that describes its ability to undergo significant plastic deformation under tensile stress before fracture. In simple words, a ductile material can be stretched or drawn into wires without breaking. For example, when copper is drawn into electrical wires, it stretches without breaking. This behavior shows the ductility. In general, ductility is of interest in three different ways. First one is for a metal working operation, indicating the amount of deformation can be applied without failure. Second one for stress calculation or prediction of severe load, indicating the ability of a material to flow plastically before fracture. Third one for indication of any changes in heat treatment or processing condition in metals. Next, we will discuss the tensile test in detail. Tensile test is nothing but it is a fundamental mechanical test used to determine how a material behaves when subjected to a uniaxial force, that is pulling force. It helps us to understand important mechanical properties such as strength, ductility and stiffness. Next, we will discuss the purpose of tensile test in detail. Tensile test is performed to determine the yield strength, UTS, Young's modulus, ductility, fracture strength and toughness. After that, we will proceed to discuss the methods used to measure the ductility and the parameters involved in its evolution. In a tensile test, ductility is determined by two important measures which indicates the extent of plastic deformation of a material can undergo before fracture. One measure is elongation, another measure is reduction in area. Elongation is indicated by the symbol epsilon. Reduction in area is indicated by the symbol Q. These parameters are obtained after the fracture by putting the specimen back together and taking the measurement. Now we will discuss the one measure, that is elongation. It is expressed in the symbol as epsilon. Elongation is nothing but it is an increase in length of a specimen when it is pulled during a tensile test. It is a measure of a ductility and it depends on the gauge length of the specimen, and it is indicated by the formula percentage of elongation is equal to LF minus L naught divided by L naught into 100. LF means final length of the specimen, L naught means initial length of the specimen. First of all, how we measure the uh, percentage of elongation in a specimen. First step is to measure the gauge length of the specimen. Mark the gauge length of the specimen before the test. A specific gauge length, that is L naught, is marked on the specimen. Usually it is a middle portion of the specimen. This is the original length where deformation is measured. For example, if the original length of is marked as 50 mm, then L naught be taken as 50 mm. If the original marked length is equal to 50 mm, L naught equal to 50 mm. Now we apply the tensile load. The specimen is placed in a universal testing machine, that is UTM machine. Now the tensile force is applied gradually. Now the specimen stretches and finally fractures. Now we move on to measure the final length of the specimen. After the fracture, the two broken pieces are carefully fitted together. Now we get the final gauge length, that is LF is measured. For example, If the final length after fracture is equal to 62 mm, then LF equal to 62 mm. LF means final gauge length. L0 means original marked length. Now LF equal to 62 mm and L0 equal to 50 mm. Substitute in the formula LF minus L0 divided by L0. LF equal to 62 mm, L0 equal to 50 mm. 62 minus 50 divided by 62 into 100, we get the values of 24 percentage. Now we get the percentage of elongation as 24 percentage. Now the another measure is reduction in area. It is a measure of ductility. Reduction in area is a measure of ductility. Reduction in area tells us how much the cross-sectional area of a specimen decreases at the point of fracture. Now we measure the reduction in area in a tensile test. First, we measure the original cross-sectional area, that is A naught. A naught equal to original cross-sectional area. Before the test, first of all, we measure the original diameter using a micrometer. For a round specimen, we measure the diameter. For a flat specimen, we measure the width and thickness. Measure the original diameter of the specimen using a micrometer for round specimen. Suppose we measure the width and thickness of the specimen. It is measured by vernier caliper for flat specimen. Now we can calculate the original area. Now we perform the tensile test by the specimen is pulled in a universal testing machine, that is UTM machine. The specimen is pulled in a universal testing machine UTM. Necking occurs where the fracture occurs. Okay, necking occurs near the fractures. The specimen finally breaks into two pieces. Then we move on to measure the final minimum area, that is AF value. After the fracture, fit the broken pieces together carefully. Measure the minimum diameter at the necked region using a micrometer. Now calculate the final minimum cross-sectional area of the specimen. For example, we take a round specimen. We can put the formula as AF equal to pi DF square divided by 4. DF is nothing but it is a minimum diameter at the fracture occurs. A0 indicates the original cross-sectional area. AF indicate the final minimum area AF. Now we can calculate the percentage in reduction in area. Percentage of reduction in area is calculated by using the formula as A0 minus AF divided by A0 into 100, where A0 equal to original cross-sectional area, AF equal to final minimum area. By using this formula A0 minus AF divided by A0 into 100, we can calculate the percentage of area in reduction. For example, we take original diameter of the specimen equal to 10 mm and the final diameter at the necking position equal to 6 mm. Now the original diameter D equal to 10 mm. Substitute in the formula A0 equal to pi DF square divided by 4. DF equal to 10 mm. It is the original diameter of the specimen. A0 equal to pi into 10 square divided by 4. We get A0 equal to 100 pi divided by 4. Substitute this A0 value in the formula. A0 minus AF divided by A0 into 100. We get 64 percentage of area of reduction in area. In this manner, we can calculate the percentage of reduction in area. Now we move on to the importance of reduction in area. Reduction in area is important because it indicates the degree of necking. More accurate measure of ductility than elongation. reduction in area is less affected by gauge length. With this, we will finish the presentation. Thank you.